some of the discussions we've been having recently on hierarchy and looking at sort of what is it that you've been working really hard at gathering requirements for what people need at the application level and how that can be layered on top of other environments. And it's at a fairly high level, but I think it should lead to some interesting discussions about some of the key problems that need to be solved and how that can be layered on top of other infrastructure. So appreciate you being able to come in and got a great presentation queued up here. Thanks.
Thanks, CJ. Jeremiah, you want to take it away?
Yeah, so I'm at Sandia National Labs in California. Let me just actually switch over to headphones here so I don't get feedback. Okay, so everyone can hopefully hear me okay.
Yeah, we can hear you pretty well.
Okay.
And your slides are up.
Okay. So at the Livermore site in California. So this is we call it a software stack model, and I'll get into what exactly we mean by that. And then we said the focus here is sort of asynchronous, what we call data effects programming. So hopping right in, at a high level, the sort of a question of why do we sort of start this in the first place? It has sort of a weird long history, somewhat unrelated to its current state. It actually started as a resilience project looking at how tasking might be used for resilience. And then as programmatic priorities changed at the Department of Energy, it got sort of spun into a load balancing and performance and asynchronous tasking framework. And the resilience component kind of got lost. So so at a high level, these are the sort of the worldview and the assumptions that we're kind of making and the basic setup for why we're doing what we're doing. So flexible granularity and data effects for tasks. Basically, for a lot of the applications, and I'll get into some of what those applications are in just a moment, granularity control is going to be one of the major key to performance. And in terms of mapping tasks and allowing a runtime to sort of steer tasks of flexible granularity where they need to go, you're going to want to understand the data effects of each task. So, as opposed to sort of your sequential imperative programming models that you have today, where you just tell the runtime to do things and you issue instructions, you're trying to build up some more meta information about the work that's actually being done in the system. And you want to give it some measure of control over the size of the tasks and the sort of the shape of the tasks, and we'll get to some of them more of that. So sort of that's sort of the assumption. And then the sort of corollaries to this is one of the approaches is going to be explicit over decomposition. And that's basically sort of what we're trying to avoid. And so the idea is that you can have over decomposition and you can have sort of multi-level, perhaps parallelism in your code in terms of mapping to, distributed memory and threads and accelerators and things like that. But the idea is the programming model should hopefully remain not too complicated. The idea being you express some sort of fundamental unit of work, and then it's the runtime's job to sort of map those efficiently. And it understands how to map those via the data effects you've expressed on the tasks. And then another thing that I'll get into, which has become sort of a focus this year, is the over decomposition approach can introduce kind of significant overheads where, because whereas you had one sort of task MPI rank to manage, you now have several tasks, which can create scheduling overheads. And so there's this another level to what we're doing called elastic tasks, which basically amounts to using Cocos or something else, or OpenMP, to create data parallelism within a task. So another level of this is we want to provide a programming model and semantic with sort of race-free execution. Another term you could use is deterministic by default. And so you have sort of a safe programming model, but in the process of having a safe programming model, you don't sort of ruin your execution model. You still allow very flexible execution patterns or execution strategies on the back end. And so the programming model is expressive and safe, but not, let's say, restrictive and preventing you from doing certain things. And if anyone has any questions, please just stop me, but I think I just created questions. So let's get into the answers. So some of the application domains. So these were the sort of drivers that led Sandia in particular to consider one of this sort of strategy for solving some of the problems. So this is my sort of joke categorization. Probably, a lot of people have probably seen this before. This is my Brunsfeld classification of Sandia applications. So there are unknown unknowns, and these are applications with dynamic, rapidly changing parallelism. And it's a load balancing, and sort of unthinkable that you would do load balancing without some sort of runtime with that just dynamic load balancing. So these are things like solid mechanics apps where they all of a sudden have to spin off a high resolution material model. There are things like particle and cell where you have these quiescence detection things, and you couldn't, it's totally dynamic. There's no way you could even guess at it, and it changes rapidly. So there's not really any persistence to exploit. You get sort of tree search in there. Possibly there's some Meyer applications that exhibit this. It's a sort of contrast and put that in sort of perspective. You can have dynamic applications, but they have persistent behavior. And this is where you might have sort of semi-static scheduling where you whatever, 100 time steps, you rebalance or repartition or do things like that. So it's dynamic. It would be nice if you had a runtime system that made that process easier for you in sort of a domain agnostic way. It's at least thinkable that you could do this in NPI plus Sultan or something like that because of sort of the persistent behavior. So you do have shifting load balance and complicated communication and computation patterns, but it's not changing so rapidly as it would be in, for example, some of the multi-scale applications. Another area where something like this could be useful, and again, you have what we call difficult knowns. Basically, you know the problem statically, and I think matrix linear algebra and some finite element matrix assembly things are like this. You know the task graph ahead of time. So it's not that your application is exhibiting dynamic behavior, but in order to implement it with efficient data flow, you might have complicated fine-grained synchronization patterns, and so you just want basically a more productive framework for expressing it. But it's not as if you, the programmer, you couldn't, given enough time, write out the task graph with pen and paper and implement it by hand. Okay, so we keep talking about DataFX programming within C++. This idea of programming with DataFX is not new. I probably could have thrown a related work slide in here. So more recently, Legion and plus its regent language has been looking at this. There was deterministic parallel Java, which is also kind of a similar idea. Even OpenMP a little bit has this sort of idea of DataFX. Basically, instead of saying spawn or fork or having explicit execution-centric constructs, you basically describe the data effects on a task, and that helps extract concurrency. So you have a programming model that sort of maintains this feel of the sequential imperative models that we had before, but it is up to a translation layer and a runtime to derive the data flow and synchronization required from the data usage relationship between the tasks. And again, remember we were saying the idea is that if you program via data effects, basically the major concern basically in what you're coding becomes problem decomposition and tuning granularity. So it's less a focus on what synchronizations do I need and where do I need to put my sync and spawn statements, but rather how do I decompose my problem to best expose parallelism or best preserve locality. So this apparently this is not going to work. Okay. Okay, I'll skip ahead and try to figure out what's going on with the presentation here. Okay. So I'll just skip ahead. I think it got out of order. So, okay, so what does this look like in terms of like the Kletsky problem that we have here? So this would be just a totally sequential imperative code. You have a matrix and you make function calls to process it. This is a tile-based code. So this is a 4x4 sort of decomposition here. What does this look like in Darma? Just to kind of give you guys an illustration. Basically, you take the code and it looks almost exactly the same. Your function calls have to be wrapped in these structs. This is just sort of a little quirk of Darma where tasks have to be types. And then you replace your calls to the function with this templated call to a function called create work that basically pushes your task into the runtime system and allows it to be delayed. Okay. So it looks almost exactly like the original Kleski code, but basically you've just done a little bit to sort of modify it and make it taskified. So that's the idea, and this is all C++. So this is all standards compliant C++, and this is just implemented in a header library. And we'll get into more details on the software stack later. Okay, so sorry, slides got over here. Again, there's sort of this notion of flexible granularity, and I think most people are at least somewhat familiar with this, or have a sort of a notion of what this means. When we talk about granularity, we're sort of encouraging people to think not just in terms of sort of the size of the task, but its shape and sort of boundaries. Your choice of granularity can be driven by many things: data locality. Maybe you want larger tasks because you have too much synchronization going on, so you need fewer tasks to synchronize. There could be pipelining, right? So you have tasks that are all doing the same thing, but you want to sort of start each of them with one stage at a time. You might be for load balance. If your tasks are too big, it's harder for you to create a load balance distribution. So you might want smaller tasks to give you more load balancing flexibility, things like that. So there's a question that we often get: is Darma a distributed memory thing or a shared memory thing, or what's the point? So we put a lot of focus on granularity, and that granularity focus could be for either shared memory or distributed memory reasons. Currently, the focus a little bit more is on distributed memory in terms of load balancing kind of being the focus. And that just has to do with the current overheads of the runtime system, which we're trying to bring down. But the ultimate goal is basically wherever tunable granularity and the synchronization patterns that sort of result from that tunable granularity, that's where we want Darma to be useful. Okay, and this is this notion of do across task parallelism as opposed to for all task parallelism. And so I don't know if people see these sort of hexagonal patterns where you can tile the space and you create this sort of double pass pattern. So you have much better data locality, but you end up with these interesting synchronization patterns between tiles. And this is this do across pattern. I think even OpenMP is considering some word like this as well. Okay, so again, this gets back to kind of what I had said before in the original slide. Basically, Darma is about you want to express a fundamental work unit targeted at the main sort of performance bottleneck of your application, and then let the runtime sort of distribute and aggregate this using its knowledge of the data effects of the tasks. I put a little compiler question mark in there in the sense of right now the human has to choose what the task actually is. In some domains or going forward in the future, it might be useful if the compiler is able to reason about how big or what the boundaries of a task should be. Okay, so we have a particle and cell example on the right there. So you have particles flying everywhere. You have to compute their trajectories, and they interact with the field and deposit charge, and you can end up with very irregular distributions. So it's not necessarily even distribution of particles across space. And so sort of really driving the point home. Should each of the boxes, how big should each of the boxes be? And the answer is, well, they should be as big as they should be to get high performance in your application. As they're saying right now, the way that we have the overheads, it's not realistic to imagine this being a single L1 size sort of block. Maybe L2 or for single thread. But as I said, the ultimate goal here is to bring the overheads of the runtime system down, such that you can really pick a very sort of fine-grained task size. And you could pick it, as I said, sort of to target some aspect of performance that you were trying to preserve. And most of those overheads I think are going to come down in terms of memoization, but it's probably sort of getting off track today. Okay. Another aspect of this is, okay, so granularity is sort of a major concern in terms of what the programming model is supposed to make easier or to shift focus onto. On the execution side, there's this notion of breadth first versus depth first execution of the graph. And this is kind of a general concept in tasking. So you see this sort of scattered around various papers. Basically, the idea that if you have a task graph and you execute it in a breadth first way, you are creating parallelism, but you're losing locality. So you're going broadly across the task graph and examining an entire level. but you're not necessarily reusing or revisiting data in sort of a local way. If you do a depth-first execution, you are preserving locality, but you're not, creating parallelism and you're possibly losing it. So there's sort of a balance here in which you want to create, preserve your locality, but also create parallelism and create additional work. And this is actually, it's most common encountered in sort of tree search problems, but it is a general aspect of many of these sort of super branchy codes, which particle and cell is a version of this. And so there is sort of a depth first versus breadth first aspect to particle and cell as well. In terms of, do I keep pushing a particle until its end, or do I move on to the next particle and come back and things like that. So it is actually sort of a general pattern that arises in many applications. So balancing the sort of breadth first versus depth first comes into the aspect of this sort of Darma execution model. And basically, and this goes to, we were saying we want safe asynchronous execution, but we want sort of high performance asynchronous execution that allows things to be flexible. So you want the runtime basically doing three things at a time. You want a task can be running, okay, and these are your ready tasks, and they can be actually executing, but they can be creating new tasks that would append to the task graph. And at the same time, you have a runtime scheduler, which is running and analyzing the DAG and deciding what tasks to happen next. So you have these three things that can be happening in parallel, and you need them to happen safely. And you don't want the application programmer to be sort of burdened with not violating conditions of how that goes. Okay, so we skipped ahead and kind of walked through the Kleski example. So there's two pieces to taking what we say sort of regular C++ code and Darmifying it. One is you have to take your data and you have to put it inside wrapper classes. This is a bit like having a future to an int. And then instead of just issuing regular function calls, you either have to create a lambda via this Darma create work lambda, excuse me. And that's kind of for sort of inline code, or you have to do the functor example, where instead of calling a function, you call the call operator of a functor via this create work. But what this has the effect of doing is the data effects and the sort of read-write usages of a piece of data are captured by calling this create work and the fact that your data was wrapped inside of this access handle object. And so you have this sort of sequential stream of tasks, but then they get translated into the task graph that you have on the right there. And all of this is embedded, as we said, sort of at the library level in C++. Via these template wrapper access handles and these create work calls. Okay, so this is where the sort of safe execution goes. As long as your sequential code, if you took out all of the create work calls and removed all the access handle wrappers, as long as that code was correct in the first place, then Darma should be correct in terms of the task graph that it generates and executes. Okay, so this is probably where it gets sort of the most unique or sort of the weirdest part now is, okay, so if we wanted to find asynchronous semantics for C++, so there are certain things that we want to be allowed in terms of the way the runtime executes, and we also want to ensure safety in the programming model. And eventually what we sort of ended up with is something that is not so different. I don't know if people have seen the Rust language and reference borrowing. But basically, when you use something, you now have permissions, which is to say the way that you're allowed to use a chunk of data. You have an immediate context and a scheduling context. And the idea is once all of your statements become asynchronous and they are not guaranteed to execute at a certain time, they can be arbitrarily sort of deferred until the data is available or the runtime decides it's a good idea to run the task. When you execute, you have two statements consecutively in the code. The second statement might not be able to execute, right? Because you don't know that the first statement even completed. And so you end up with this sort of, this world of deferred execution and asynchronous semantics. So the idea is that once you use something, and so we have this closure, which is a create work, Then you have a continuation, which is the code that follows the call to a create work that creates a task. So the closures 1 and 2 can be sort of arbitrarily deferred, right? So you're creating a task, you're pushing another runtime system, and you're saying, once data flow and dependencies are satisfied, go ahead and run the task. The task itself is executing just as regular C++. So create work call is a library call. And then in the next statement, you're again just executing C++ code. So the applications, it issued this call to create work, and it sent its task off to the runtime system, but it doesn't actually know, what the runtime system is doing. So the semantics of this is basically that if you had modify permissions on this access handle V, and you created work that read it, for the remainder of that task, you could no longer modify it, because doing so, closure 1 can be arbitrarily deferred, and doing so would basically violate the sequential ordering of your operations. And so the semantics of this is now you still have scheduling permissions, so you can create tasks that modify V, but in the immediate context and in the continuations, you're no longer allowed to modify V. All you can do is read it. If you want to modify V later, you can do that, but you have to create another task, and that pushes a task into the runtime system. But that task, because it was created with a create work call, now the runtime system is able to reason about the dependencies and preserve the synchronization and data flow. And so in the context of closure 3, and that's or closure 2, excuse me, at point 3, okay, now you would be back to having immediate privileges that allow you to modify V. Hopefully this is making sense to people. Like I said, it's a little subtle the first time through. But like I said, we sort of arrived at this, and then after we sort of developed this, we realized there are some similarities to Rust and some other languages that are kind of sharing this idea. So it's a consequence of needing sort of race-free, safe, deterministic by default programming model, but then also allowing the runtime on the back end to sort of arbitrarily defer operations and schedule things asynchronously.
Do you want to comment briefly on the sequential semantic there, just to connect the dots?
So this has to produce an answer that was equivalent to this thing executing sequentially without the create work calls or the access handle. And so if you have a read in closure 1 or task 1, and then you have a modify in task 2, right? It can't occur until after the read is finished. Or unless you've made a copy. So the backend is also free to make copies that would preserve the sequential semantics. So it has to produce an answer
for this
sequential execution.
For the sake of debugging in your implementation, do you have something that essentially enforces a given specific sequential order for the sake of debugging, even though relaxations of that are certainly possible?
Yeah, so the common debug mode is we have a version of this which is not distributed. It's just shared memory only, and you can set a depth parameter to 1, and that essentially forces it to do depth first execution, or sorry, breadth parameter to 1. And so whenever it reaches a create work, it just executes it immediately and moves on.
Okay.
Yeah, so there's a debug mode for that.
Often kind of hard to live without that.
Yeah. No, it's Yes, you should always debug the sequential version of your C++ code first, and then throw different execution in. So, again, getting back, one of sort of the major goals here was, we said sort of balancing depth versus breadth first execution of the programming model. Okay, again, the semantics basically allow the runtime to choose sort of any task ordering or any execution order here. So, if the runtime sees fit and it wants to just start immediately executing the task, it can. Another aspect of this, though, is so we said the access handle was a little bit like a future, in the sense of that sort of it's a piece of data the runtime promises to provide you at some point in the future. The major difference here, though, in our sort of access handle or asynchronous pointers are there's no get method, there's no block method. You can never take a deferred piece of data and force the runtime to block and wait for it. And so if you have data that you want to access and you don't have immediate permissions on it, the only way to access it is to create a task, basically called create work. And so this creates sort of a non-blocking model. It also means that there's no context switching required, so the runtime is not required. Whatever runtime is supporting this or whatever hardware is supporting this is not required to implement context switching. And then, like we said, this creates a balance between sort of depth first versus breadth first execution in terms of prioritizing what work you do next. Okay, this is all safe. So the programmer can't do anything to mess things up. The runtime is free to schedule and analyze the DAG and append new tasks and run ready tasks sort of freely as it wants, without worrying too much about conflicts. And so that's sort of the programming model, and the semantics feeding into the execution model and the way we want things to happen. Okay, so sort of at a higher level, so programmatically. So we refer to Darma as a software stack model. And essentially what this means is what we want as much as possible is to define a programming model embedded in C++. This would feed into sort of a glue layer that maps the execution model semantics via a task graph to sort of arbitrary dynamic runtimes that might be able to implement this, to sort of encourage collaboration and explore for different modes of operation. So you have the application, and then it implements via the Darma header library. This contains a translation layer, which, as we said, captures data effects and data usages, does the dependency analysis, converts it to a task graph representation. That task graph gets fed off to a glue code, which then needs to map out to the different runtimes. So what sort of things have we done? So Tarn++, we test at scale. That was an activity last year. That glue code ended up being a little bit larger than we expected. We are currently working on an MPI plus OpenMP reference implementation. And again, that one's kind of a full, this glue code we'll say is pretty full featured. So there's quite a bit in it to implement all the task graph functionality. HPX is another example. HPX is a very thin glue code because it provides basically feature-like constructs, and it was pretty easy to map the Darma semantics onto features as they are implemented in HPX. And then we have a couple on-node.
Who did you work with on the HPX thing, if I can ask?
I think it was mostly, so there's another person on the team, David Holman, and he's been mostly doing the HPX stuff. I think he mostly worked with Hartmut Kaiser, but then we also worked with Thomas Sterling a little bit on their version of HPX. But the version that we had working, I think, was the LSU version 3.0.
Okay.
Yeah, and then we have an on-node version, which sort of still feels, it'll be the exact same code that you would be able to take and run in distributed memory, but it actually just runs on-node via threads. Okay, and so that's sort of what I mean by sort of software stack model. Basically, the idea being that you have a C++ header library which can express data effects and express your concurrency in sort of a standardized way. And then it's up to all these different dynamic runtime systems to interpret that concurrency specification and map them as efficiently as possible to its particular runtime system. Okay, so most of what I was introducing was sort of most relevant for on-node tasking, and sort of safe execution in terms of thread level parallelism. At the distributed sort of memory level, and it doesn't have to be distributed memory. So you still might be using these constructs even if you're trying to generate on-node parallelism. But this will be the common mode of operation for large sort of SPMD applications. So not only you can create sort of one-off access handles, you can also create collections of data, and basically it's just an indexed object. And these index ranges can be quite large, and then they can sort of get mapped over the entire system. And so again, if there are any Legion people on, sort of a similar idea. They have index ranges and field spaces and things like that. So the index range is just an application input parameter. It doesn't need necessarily to have any particular relationship to the number of ranks or the number of nodes that you have in your system. And again, this is sort of the parameter that would tune your granularity. So if you had a big distributed array of data and you wanted to chunk it up and partition it, you would choose the size of your index range such that your sort of pieces or chunks were the right size you need for load balancing, or like we said, or cache locality, etc. Okay. So just to have a few results in here, sort of on the notion of granularity control. Going back to our particle and cell application, this was one of the major problems driving our work last year. So these results are a little old, so we have some new ones coming up from the OpenMP excuse me, reference implementation. So we said you could think about doing a multi-level decomposition of the problem and mapping each of these multi-level decompositions to specific hardware resources. What we were sort of trying to push or pursue, and sort of still evaluating, is again to say, well, let's create a fundamental work unit, and then the runtime that knows the hardware and understands the data effects of those fundamental work units, let it kind of sort of maybe build the hierarchical mapping itself, in terms of mapping things to cores and doing the load balancing and shifting things around. So the major experiment was load balancing. So this is already composed. So it's you have multiple tasks per core. So it's the most direct comparison would be 1 MPI rank per core. And now we're saying over decompose. So you have multiple tasks per core. And in the process, you can get communication pipelining, because while one of your patches of particles is executing, you can be doing the communication for the other ones. And then you have load balancing flexibility. So if some of your patches are really heavyweight, you can trade those around in load balancing phases. So if you have an over decomposition factor of 1, so you have 1 task per core, what you end up seeing is there's a lot of idle time. And that's the sort of gray on the top there. So there's not a lot of utilization. And then you have these sort of peaks of data transfer. And so you're not really spreading out your communication. It's not, if you go to an over decomposition factor of 8, for example, you can see that your work is much more spread out. It's much more balanced across the system. The percent utilization of your system increases generally, and then your data transfers are not so packed into this one tight little space. Very observant people will say, well, but your total runtime didn't really change at all. This is super compressed, so don't read too much into the 2.19 versus 2.17 seconds there. So the picture itself is sort of correct and illustrates what we're going for. And as I said, we're sort of still fighting to bring some of the overheads down. But notionally illustrates the point of the over decomposition factor. And again, sort of another perspective on the load balancing. So this is on Trinity. So we went up to 2,000 and 4,000 nodes on Trinity, both on the KNL and Haswell partitions. So with no load balancing on this particle and cell code, at least at the smaller scales, right, we're doing way better. And so the over decomposition approach is doing a pretty good job of achieving load balance. The scalability of the load balancing heuristics in Charm++ start to taper off towards the end. And so again, the space, it really becomes just a matter of controlling overheads and finding good heuristics for the load balancer that aren't too expensive. But at the very least, you can see compute intensity over time. So you run the load balancer a couple of times, and all of a sudden your compute intensity is way up. So you have a much more balanced distribution of work across the system. You did have another option for how to do this. This was over decomposition. So you just created tasks, you created a fundamental work unit, and then you let the runtime system figure it out. You could have done this explicitly at the application level using MPI plus Ultian. So we ran the load balancer once every 100 iterations. So this was this sort of known unknowns case. So you knew there was going to be load imbalance in your application. but it was going to be persistent. So this wasn't where you didn't need work stealing, you didn't need super dynamic load balancing on every single iteration of what you were doing. So the primary advantage here is there's no remeshing, there's no resetting up of your data structures, and so load balancing and checking for load balancing is actually a somewhat lightweight operation. It becomes a little bit heavyweight if you have to start migrating tasks, but you don't fundamentally disturb your algorithm, which is that once you've expressed your algorithm and defined serialization of your objects, you get sort of load balancing for free. So whatever load balancing heuristics or performance counters or whatever you might want to tell your runtime system to consider in doing its load balance, is just there. So you don't have to sort of re-implement it for each application. There were two things that were going to be critical in lowering overheads going forward, which is really what we're trying to figure out how to do. One of them we sort of alluded to, and I won't go too much into detail there, is sort of memoization and using the sort of persistent nature of a lot of these scientific computing codes to create sort of a more lightweight synchronization graph as opposed to doing full-blown dependency analysis on each and every iteration. But another critical piece for us this year is this notion of over-decomposing nodes as opposed to over-decomposing cores. So previously, when people talked about over-decomposition, particularly in the context of things like Darma++, you had 4 or 8 tasks per core. That's way too many. And so what we're aiming for here is, so we have integrated with Cocoa. So this project is pretty closely linked to the Cocoa project. And so now tasks can be expressed elastically, which is to say there's data parallelism within the task, and the Darma runtime system is capable of allocating a certain number of cores to each task. So you have sort of 2 levels of dynamic behavior in what you're doing. You can over-decompose, and you can move tasks around the system in terms of controlling the number of tasks on a node. But even then, if you end up with tasks of varying sizes or massively different sizes on a node together, you can shift around how many cores you actually allocate to each one. And so instead of having a huge number of tasks, multiple tasks per core, you can still over decompose and have full balancing flexibility that way. But you're using Cocoa, so the total number of tasks on the system is drastically reduced. I think most people can appreciate what's going on here, so we just have that silly little figure on the side there to show that as you increase your over decomposition factor, right? What started out as mostly computation, sort of rapidly gets swallowed up by scheduling and communication overheads. So yeah. Skipping ahead, it's like I said, what we're sort of primarily working on right now is taking some of the lessons learned from our Darma++ exercise and trying to put them in an MPI plus OpenMP plus Cocoa's reference implementation, and in particular defining MPI interoperability, which I guess I won't really spend much time talking about, but basically setting Darma up as, instead of being sort of in charge and the only thing running on the system, you can branch it off and run isolated Darma kernels within a larger application. Sort of our other activity this year, aside from the Sandia programmatic things, is not so much me, but a thing on the team member, David Holman, is pretty active on the C++ committee, and trying to push some of these asynchronous semantics idea into sort of library level things that might be included in the C++ standard, probably not 20, but maybe further down the line. And then again, less closely related to Darma, but still sort of bringing the Darma worldview to the C++ committee is also the parallel executors. And various other C++ activities. So so there's sort of an alternate goal here, which of trying to build these libraries and demonstrate them with sort of custom libraries that we have, but also trying to figure out what sort of semantics or constructs might be useful in parallelism technical specifications going forward for the C++ standard. Okay, so that was the introduction. I don't know if there are questions out there.
Thanks. Everybody's jumping in all at once.
Yeah.
This is. Can you hear me? Okay.
Yes.
John Badiscombe from CSCS, one of the HPX guys. I was curious early on in the slide. It must have been near the beginning somewhere. You were talking about how the tasks are before the scheduling takes place. You were talking about permissions on tasks, and I was kind of curious because in C++ we have the const keyword. And so you can say that a task is non-modifiable effectively, or you can say that the data is non-modifiable by passing it as a const object rather than. So how does it work that you have these permissions on tasks? It seemed a little bit. The word that came to mind was over-engineered. Why the permissions?
So we actually do use the const keyword. So if there's extra time, I was going to hop people over to our online tutorial where you can punch some editable examples. So there's in those functors that we said. So you have a create work, and instead of calling a function call now, you have a create work, which is templated on a functor type, whose call operator actually executes the task. If you haven't, you can map those directly to regular C++ parameters. So you can have a task which is callable with access handles, but doesn't actually have any access handles in itself. And if they're const, then Darma can interpret those as read-only permissions. So in terms of explicitly specifying permissions, that's actually really only needed if you have an access handle mapped to an access handle and you would want to downgrade. So we actually do use consts and the reference qualifiers on the types and do some type deduction about how you're actually using your data and what the runtime system needs to know in terms of dependencies.
Okay, so that means effectively the data objects that are passed around, you actually access them via these access handles rather than by passing pointers directly to objects and things.
Yeah, so anything that you want to be tracked with dependency analysis has to be inside of an access handle. You can. Oh, sorry. Go ahead.
Well, that would lead me on to the next question then, because what you have on the graph you're showing, actually, you've got new tasks being appended, then you've got a scheduling analyze DAG, and then you've got the running tasks. Now, do you actually run the analysis of the DAG part on a separate thread effectively so that you're preparing which each core effectively finishes a task and then it says, I need the next bit of work. And it can either pull that directly from the DAG itself or somebody could have prepared it. Is the scheduler running as an extra task that's preparing who gets what next?
So this is an execution sort of model only. It's not required to implement things a certain way. So in general, mostly when we implement this, yes, we have worker threads running and they're pulling off of queues and they're not really doing any logic. They're just being told, here's a task that you can run. And then you have one or a few threads that are actually running a scheduler, checking for dependencies and pushing communication forward and things like that. So the figure there, sorry, maybe I didn't explain very well. So those are just sort of the operations you could think about potentially happening in parallel. And so you want sort of nice guarantees about what they're allowed to do and when, so you're not creating headaches for yourself. They don't have to happen in parallel, so you're not required to implement the execution model in that way. Sorry, does that make sense?
So who would own the scheduler in the layer cake software layer cake? Is that in Darma or is it beneath Darma?
It's beneath. So when you call create work or you create
John has to do it.
Whoever, yeah. If you were implementing or working on the HPX backend, for example, yeah, you would be responsible for it. You would be given, like we said, dependencies. You wouldn't necessarily be given, the read write and the sequential specification. But yes, you would be responsible for determining that a task is ready and then passing it into a queue to be executed.
So the reason I asked is because I've been cleaning up one of the schedulers in HPX at the moment, and I'm finding that the more logic I put into the scheduler, then really the nastier things get. And keeping it as simple as possible so that you just have queues with work. Now, of course, the way HPX specifies the dependencies is slightly different. So in a way, it's a little easier because we don't have to analyze the DAG. The DAG kind of just happens.
Yeah.
Because like continuations, when a task completes, it automatically triggers anything that depends on it if that thing is ready to run. And so you don't have to kind of analyze it. It's just a question of choosing which one you want to execute next. And so I was thinking as you were presenting this, that actually doing some of that on a separate thread, there might be some advantage to doing that, because there's sometimes decisions like I could run a task that's ready now, or I could actually run a different one which I know I might have to wait a second for, but it's got more work and it would use the cache better and things like that. And so there's trade-offs to be made. And the more logic you put into the sort of raw scheduler, then the more chances there are of delaying things. So I was just curious as to how you do that.
And that goes into the depth first versus breadth first. You can defer work and then build up a bigger picture of your task graph, and you have more parallelism and more options to choose from in terms of how you execute. Or you can just go the depth first route where you just say, I'm just going to execute work as I get it, and sort of greedily push through tasks.
So again, to clarify, what you're passing down, it might be interesting to see if you have this in your tutorial or wherever, sort of what your interfaces look like for what it is that you pass down to the layers beneath you. So it looks like you're passing down a DAG, which basically, and are those nodes only tasks, or do they also involve things like memory management and synchronization? Data movement.
It is just tasks and flow dependencies.
Okay, so and then it's up to the lower layers to figure out, given these higher level, Darma matrix data structures, how to implement them and realize those on a given target platform in terms of distributing them and allocating the memory and binding it to specific resources, etc.
Yeah.
And that's expressed only as, those are expressed only as operands of the tasks in the DAG?
Yeah, correct. So you have a task, which is the actual code to execute, and then you have a sequence of input dependencies, and they're either flow dependencies, which is to say it's data that you need to be made available, or it's anti-flow dependencies, which is to say you need to somehow resolve the fact that somebody's reading this potentially at the same time that you're writing it. And that's essentially what's passed down. So if you had a greedy schedule, you could implement this quite easily, because it's just, you just basically have a join counter on all of your tasks. As soon as all of its input dependencies are satisfied, you queue it up as ready to run. Or if you wanted to do, we were discussing more advanced scheduling logic, where you actually tried to create a schedule with the fewest holes possible. That would be more complicated, but the information is there to do it.
I have another quick question. I don't know. I'm Oscar Hernandez from Oak Ridge, and I also have a colleague here while in the call. We have an application that I'm looking at the diagram that you have here in the slide, where you have like some DGEMs here, and you're executing them as part of your tasking, the way you're as a tasks. One question I have is, are these DGEMs that you have in this diagram run is it like data parallel inside the DGEM, or is it like a sequential DGEMs in here?
They can be parallel, and like I said, one of the main things that we were trying to work on this year, in particular with the MPI, was OpenMP backend.
Yeah.
So you can create an MPI communicator and you pass it off, and your code just happily runs, and it doesn't really care what its communicator was. It's historically been a little harder to think of using OpenMP that way.
Right.
But that's essentially the idea now, is that with the multi-level OpenMP, you basically you create a little parallel region with a well-defined number of threads, and then you call off to MKL or whatever.
Yeah.
And then it doesn't know its sort of thread environment. It can query its depth or whatever, but it basically just runs on the threads that it was given by the Darma runtime.
Yeah. So the problem statement that we have is like we have an application where we have a lot of that follows a strategy where we have these dgems, but each of these dgems may need different number of threads. And for example, and then it becomes this issue that then these tasks here, they also need like different resources, basically in terms of threading and so on. And how does that gets mapped to the concept of when you schedule these tasks. Currently, for example, in methods like OpenMP, they kind of assume that, well, one way of looking at tasks is like, a thread will execute a unit of work there. And one of the mechanisms we have is that nested parallelism inside the task. But the problem is that, is the overhead creation of that nested parallelism, and that can make it performance. And so you also brought the topic as well of elastic tasks, and I wanted to understand more or less, what is this strategy of scheduling things that have like different resources in the context of threads, like in this specifically this use case. What will be this? What strategy do you envision to pursue?
So there's two sides to it. One is just the engineering problem, which you sort of touched on, of even just being able to call something that has an OpenMP parallel 4 in it, and tuning the number of threads in the actual cores it uses to execute. Yeah. And even once you have that sort of engineering problem solved, which, like I said, we sort of do, but not. OpenMP doesn't necessarily allow us to do things exactly the way that we'd want to do it.
Yes.
It's okay for what we want to do now.
Yeah.
The other problem that you have is you have to express a cost model for the elasticity of your task, or a performance model basically for your task. And that we haven't fully defined right now. It's just basically it's a little keyword that you tack onto your task to say, if you could run on this many threads if you wanted to, and you would still run efficiently. Mm-hmm. But yeah, basically the runtime, and there are various scheduling algorithms out there in the literature that basically say you start with one thread and you keep adding threads to your task. And then, at some point performance is going to taper off. So there's going to be some optimal number of threads to use for executing your task.
Yes. Yes.
And yeah, so the scheduling algorithms are actually out there in literature. I mean, we haven't implemented any of them, but they exist. So so more fundamentally, the problem is how do you get someone who's an application person who's a good understanding of how they think that kernel will perform in parallel, and how do they express the elasticity to the runtime system in a way. So that is absolutely an unsolved problem.
Okay.
So let me see if I can just clarify that. I think that you're saying you're leaving all that job of the distribution of the work, the binding and the scheduling, et cetera, to the lower levels. You're trying to provide a DAG, a fully materialized DAG, to those lower levels, and pass on from the user whatever guidance that you can about how that might work and what the cost or performance models are. And then it's up to them as to whether they're going to use a hierarchical implementation or how they're going to deal with the hierarchical expression of parallelism in areas like OpenMP and so on. You talked about doing some of that in your runtime, and so it wasn't clear what the relative division of responsibilities was that you're doing in your runtime versus what you're expecting out of what's below you?
Sure. So in terms of, let's say we're going to use Cocos, you would create a Darma task, and then the first thing the only thing you would do inside that task is call Cocos parallel for, or Cocos parallel reduce, or something like that. You can imagine us trying to basically merge those constructs, and so you wouldn't even have to call Cocos parallel for, you could just call Darma parallel for, and it would both create a Darma task and invoke the Cocos parallel for inside of the task. And so you've basically written one single level sort of piece of code, but you've got multiple levels of parallelism there, data parallelism within the Cocos kernel, and then the fact that you have this task which is deferrable and pass parallel potentially with other things. But yeah, but the questions to be answered by the runtime are when do I actually run this task, and how many threads and which cores do I use to run the Cocos parallel for.
Mm-hmm.
So
that's essentially binding and ordering.
Yes. So that is up to the backend runtime. The big question is how do you communicate the degree of parallelism within a task? Sort of the default mode right now is just, okay, run as many threads and assume that the task scales. But if you had a task which, whatever you wanted, it would run well with 4 threads, but it wouldn't run particularly well if you had 12 threads, for example. How do you communicate that metrics to the runtime system?
Hey guys, we should.
Do you allow dynamic task generation?
What do you mean? A tasks being created by other tasks?
Can a task create a task?
Yes.
We should probably wrap this up. We've run out of time. It was a really good presentation, Jeremy. Thank you. Excellent. I have recorded and we'll post it right after this for those who want to refer to it. But thanks, Jeremy. Much appreciated.
Yeah, and if you go to the end of the slide, there were a couple of links to tutorials. So if people, I didn't go deep into the details of actually coding and walking through code examples, but those are all online for people who want to walk through those.
And I did put a link to the tutorial on the wiki page too. So please drop me a note if you have any trouble getting hold of it. But thank you, Jeremy. Really good talk, and lots of good questions.
Yeah, thanks for inviting me.
Thanks. Appreciate it.
And if you don't mind, Jeremy, maybe you could look over the minutes that I took, and you can feel free to edit those and clean those up.